This video from my Skills and Environment series is going to be focused on altitude diving. There are quite a few questions regarding altitude diving that you might see popping up in the dive theory exams for the PADI Pro courses. In a number of different sections of the theory exams, you could get questions about altitude diving in the equipment of diving, in physics, but the most likely place you'll find them is in the Skills and the Environment section. So, at altitude, the atmospheric pressure is lower than it is at sea level. This means that when we ascend from depth, when we ascend from a dive to the surface, we experience a greater proportional pressure change than when diving at sea level. So the difference between the pressure we were under when we are at depth and the pressure we are now under is a greater proportional change when you're diving at altitude compared to sea level. Here is a chart showing pressures at different altitudes. It might be a little bit confusing because you're very used to seeing things in atmospheres, whereas the pressure on this chart is in kilopascals. But it's actually fairly simple. Let me just explain it to you. At 0 meters sea level, the pressure is approximately 100 kilopascals, which in atmospheres we can call 1. Basically, divide by 100. It's not quite perfectly correct to say that, but it's close enough. So what would the atmospheric pressure be if you were at 2,000 meters, approximately 6,000 feet? Well, it would be 80 kilopascals, which is 0.8 atmospheres. So that's what we mean by the ambient atmospheric pressure being lower at altitude than it is at sea level. The easiest way to understand it when we think about the relevance of the atmospheric pressure with regards to diving is that it's all about pressure gradients. If we allow there to be too high a pressure gradient between the pressure of the gas dissolved in our body and the pressure surrounding us, that is when it's possible to get DCS. So gradient is this very important word. A gradient is an incline or a slope. You know that when walking up a steep slope, you get more tired than walking on level ground. The greater the gradient, the steeper the slope, the more tired and out of breath you get as you try to walk up it. Well, likewise, the greater the gradient of pressure in our body compared to the pressure surrounding us, the greater the chance of getting DCS. So let's try and use a worked example to better understand this concept. If you go on a dive and based on your dive profile, at the time you surface, the gas pressure in your body, in your tissues, is 1.4 atmospheres of gas pressure. Obviously, that's a mixture of different gases, mainly nitrogen and oxygen, but the total gas pressure of dissolved gas in your body is 1.4 atmospheres of dissolved gas. You've absorbed a load of gas during this dive. Now, let's try and pull up a graph to help us visualize the pressure gradient between the pressure surrounding you at the surface and the gas pressure in your tissues. So what we have here is the starting point, the gas pressure in our tissues at the time we surface, and that's 1.4 atmospheres. If we're diving at sea level, the atmospheric pressure surrounding us is 1 atmosphere. So the pressure gradient would be this incline or slope that you see here. The pressure gradient, the difference in pressure between the pressure in our body, the gas pressure in our body, and the gas pressure surrounding us. Let's now think of another graph. Let's imagine the same scenario. You surface from a dive with 1.4 atmospheres of gas tissue pressure in your body, but this time you're diving at an altitude of 2,000 meters, 6,000 feet. We're surfacing with the same gas pressure in our tissues, in our body, as we used in the previous example, we have 1.4 atmospheres of gas pressure in our bodies. But when we surface at an altitude of 2,000 meters, approximately 6,000 feet, the pressure surrounding us would be only 0.8 atmospheres. So this gradient, this incline or slope, is steeper. It is a greater pressure gradient between the pressure of the gas absorbed into our tissues and the pressure surrounding us. And the greater the gradient, the more chance there is of getting DCS. Let's quickly put these two slopes on the same graph next to each other, and you can see that the red line is a lot steeper than the blue line. The pressure gradient when we surfaced at an altitude of 2,000 meters was much greater than the pressure gradient when we surfaced at sea level, and that is the main reason for a lot of special rules that you have to follow if you are diving at altitude, which is what we will now go on and look at. What rules do we need to be aware of in order to successfully answer the altitude questions that you could be faced with in the theory exam? One rule is that you need to convert the actual depth you plan to dive to a theoretical depth, which is based on the altitude you are at. And it's important to realize that the conversion to a theoretical depth is based on the altitude you're at. It's not based on the barometric pressure. It is based on the altitude you're at. These two things have obviously a very close relationship, but the tables use altitude when you are calculating your theoretical depths. Let's have a look at a table. Before we have a look at a table, the depth of your safety stop may also need to be adjusted, and you find that on the same table. So now let's look at the table. Here we have an altitude table allowing you to convert the actual depth you plan to dive to a theoretical depth based on your altitude. So for example, if we were diving at an altitude of 10,000 feet and we planned to dive to 80 feet, we should plan our dive as though we are actually going to be diving to 116 feet. 116 feet would be our theoretical depth. So let's actually imagine how that would affect our dive planning. We are diving to 80 feet. If we were doing that at sea level using the RDP, this is just a cropped version of it. Hopefully you're very familiar with this table. If we were diving to 80 feet at sea level, our NDL would be 30 minutes. But because we're planning on doing this dive at 10,000 feet, even though we are only diving to 80 feet, we've got to plan the dive as though we're diving to 116 feet, which using an RDP table you'd be required to round that up, so you'd round it up to 120 feet, and you'd realize that your NDL would be only 13 minutes. So an 80-foot dive at sea level, you'd have an NDL of 30 minutes. An 80-foot dive at 10,000 feet, your NDL would be drastically reduced to only 13 minutes. In addition to that, looking at the safety stop bar at the very bottom of the screen here, you realize that at 10,000 feet, the depth at which you would do your safety stop would be only 10 feet. We all know that a normal safety stop at sea level you do at 15 feet for 3 minutes. Well, at 10,000 feet, if you were doing a dive, your 3-minute safety stop would take place at only 10 feet. The reduced partial pressure of oxygen at altitude will cause you to feel hypoxic more easily. Hypoxic means not having enough oxygen, feeling like you don't have enough oxygen. So that reduced pressure of oxygen at altitude means that you should be aware of this fact, and you should limit your exercise, your exertion. In surface swim a little bit slower, take it a little bit easier than you might at sea level. After your surface swim, maybe out to the point at which you plan to descend, Maybe give yourself a couple of extra minutes to just rest and recover and get your breath back before you descend. When surfacing from a dive at altitude, swimming back to the shore, just take it that little bit easier, go a little bit slower. Another rule is that dives above 8,000 feet require you to arrive at altitude 6 hours before the dive. It is actually recommended you do this for any altitude, though. So let's imagine that we're not diving to 8,000 feet, which requires a 6-hour interval before the dive. Let's imagine that we're diving at an altitude less than that, and we want to dive immediately. So if you do not do a 6-hour acclimatization period between arriving at altitude and diving, then you need to plan your dive as though it's a repetitive dive. You should actually count 2 pressure groups for every 1,000 feet of altitude, and assume you're starting your dive in that pressure group. Again, to help you understand this, let's look at a worked example. So we're going to imagine that we're incredibly rich and we're able to afford to have a chopper fly us up to a lake at 6,000 feet, 2,000 meters, and we want to go down and do a dive immediately to 60 feet because time is money. No time to wait around for 6 hours. What would our NDL be for this 60-foot dive if we're diving in a mountain lake at 2,000 meters? Well, firstly, what we need to do is count 2 pressure groups for every 1,000 feet. So 6,000 feet, 2 pressure groups. We need to count 12 pressure groups and consider that to be our starting pressure group. So counting down 12 pressure groups, you realize that you should assume that you are in pressure group L at the start of this dive because you're diving at 6,000 feet. So that's one part of the dive planning we need to consider. The next part is to think about our theoretical depth. We are wanting to dive to 60 feet at an altitude of 6,000 feet, so we should plan our dive as though we're actually going to be going to 75 feet. So using these 2 bits of information, we're in pressure group L at the start of the dive, and we are diving to a theoretical depth of 75 feet. What would our NDL be, our adjusted no decompression limit? So pressure group L, theoretical depth of 75 feet, we need to round that up to 80 feet using a table, and we look at the intersection of that and would see that our NDL for the dive, our adjusted no decompression limit for a dive to 60 feet at an altitude of 6,000 feet, if we were to immediately dive after arriving at that altitude, we would only be able to spend 8 minutes on that dive. When you're diving at altitude, your ascent rate should be halved. Hopefully you know that the normal maximum ascent rate for a dive when you're diving at sea level is 60 feet or 18 meters per minute. You would have learnt that in your open water diver course. So when diving at altitude, if we're halving it, that means our maximum ascent rate should only be 30 feet or 9 meters per minute. We're always going to ascend much more slowly when we're diving at altitude than we would at sea level. Make no more than 2 altitude dives in a day. If you're going to be diving at 2 different altitudes in the same day, you should dive at the higher altitude first. So imagining you want to dive in a lake that's at 6,000 feet and you want to dive in a lake that's at 5,000 feet. Dive in the lake that's at 6,000 feet first, then descend and dive in a lake in the 5,000 foot lake. Obviously, it tends to often be colder at altitude, so you need to allow ample time to rewarm between dives. And don't go to altitude to dive immediately after diving at sea level. You need to follow the flying before diving rules. Basically, going up to altitude is almost the same as getting in a plane and flying, depending upon what altitude you go to. So just like never jump straight in a plane and fly after a dive, never drive up to altitude immediately after diving at sea level. When using nitrox at altitude, you should plan your NDL as though you were using air. So whilst using nitrox at altitude can definitely be beneficial, the higher amounts of oxygen are going to help you feel less hypoxic, etc., etc., you shouldn't actually take advantage of the other benefits of nitrox, which when at sea level, obviously, nitrox allows us to extend our NDL. When using nitrox at altitude, we shouldn't use nitrox tables to extend our NDL. We should just use the standard air RDP to calculate our NDLs using the theoretical depths we've already looked at. The final study tip I've got for you regarding altitude diving is to read the altitude diving chapter in the PADI Advanced Open Water Manual or the Altitude Diving Specialty Manual. There are going to be questions on altitude diving in your exams. It's really going to help you to read that chapter and be familiar with what is in it.